Hello, everyone. Can you hear me? Hello. Hello once again. Can you hear me? Are you online?
Good afternoon. We can hear you.
Okay. We will be waiting for a little bit more, actually, because there are only 6 people currently on, and then we'll start. Okay, we can start now. Thank you for joining in. Okay. Today we consider the maximum likelihood method once again in little bit more general terms, and in particular we'll see how this statistical maximum likelihood method can correspond to methods of data science. After all, our course is called Data Science in Finance. So let us call it maximum likelihood estimation, advanced topics. As a quick recap, what have we been doing last time? You remember? We considered, in the simplest case, we considered a geometric Brownian motion, GBM, a process ST given by stochastic differential equation, dST, being equal to some trend, for example, mu t times st, where this is a deterministic function, dt, plus...
Can I ask a question?
Yes?
You will upload this lecture later on Moodle, right?
Would you like to ask now or later on?
No, like you're recording and you will upload it later, right? Later.
Ah, okay. You see, yes, I'm recording, but the problem is, you can't, as far as I understand, you can't, or you have significant difficulties with playing back those recordings. So for that reason, I think what we can do, we can probably do slides as well as our recordings. But yes, I will upload it anyway, and I will produce a slides as a summary for you in case if someone has difficulties getting through the recordings. Okay?
Okay, thank you.
So, continuing with the geometric Brownian motion, we have plus some sigma t st dwt here. So what is important is that we have a factor st in both actually the trend and the volatility. Sigma t is also a deterministic function, or in particular it could be a constant. And then with this setup, especially if it is a constant, then it is very easy. So in the simplest case, we would say mu t equals to some constant mu bar, sigma t equals to some constant sigma bar. We constructed the likelihood function with the objective of statistically estimating those unknown parameters. So if we have a vector q of our unknown parameters mu and sigma, which need to be estimated, then how we do it? We construct the likelihood function after some transforms. We constructed it in a log space, but in general, the likelihood function, which depends on our vector of unknown parameters q, would be, let's say it is very convenient to do a log likelihood function from the very beginning. And you remember what it was. If we had time series of our process S0 and so on Si and so on Sn, corresponding to time instance T0 and so on Tn, then our log likelihood function would look like sum from I equals to 1 to n, the probability density of our parameter of our value Si conditional on, first of all, the previous one, Si minus 1, and the value of unknown parameters q, log, sum of logs, and this likelihood function had to be maximized in general over the vector of unknown parameters q. And then the estimated vector of parameters would be precisely the argument of maximum of L of q over, in general, all q, in this case belonging to R2. That was our setup. You remember why our probability density here would be conditioned only on Si minus 1. Which property, can we repeat please this point? In general, it wouldn't be conditioned on Si minus 1 only. It would be conditioned on all previous values. Let's say S0 and so on, Si minus 1. Nevertheless, we used a certain property which allowed us to claim that we are conditioning on Si minus 1 only. Do you remember which property is it? A quick quiz. You remember we were talking about the Markovian property of our stochastic process? Which basically says that if, let's say, Si minus 1 is the last observed value of the process, then distribution of probability density function, let's say P of S, depends on Si minus 1 only, and Q, of course, but not on the previous values let's say S0 and so on, Si minus 2. And because of this Markovian property, we can really write the dependency on Si minus 1 only here. Okay? Which simplifies our task very significantly, at least for the one-dimensional stochastic differential equation. For the geometric Brownian motion, we could construct this density very easily, actually. So what we did, if you remember, we did a slight modification. So instead of L of Q, we would do a log transform in this particular case. not only log transform in the sense that we are taking log of p, but we would also be considering log of s. So there was another function L of q, which would be sum from I1 to n log of another density of actually log of Si divided by Si minus 1, because Si minus 1 is already here. We don't need to condition it on Si minus 1, and we only condition it on Q. And this function P of log of Si, log of Si over Si minus 1 conditioned on Q, because this log is normally distributed with the mean equals to being equal to mu minus sigma squared halved times the length of the interval, which we call tau, and the standard deviation being equal to sigma square root of tau, and tau being the temporal length of the interval, ti minus 1. Then for this reason, it is very easy to say what this function is. It is 1 divided by square root of 2 pi tau sigma outside of the square root exponent of minus 1 divided by 2 tau sigma squared bar, our log of Si over Si minus 1 minus the expected value, which is mu bar minus sigma bar squared halved times tau squared, right? And with this expression for our density, we then constructed explicit maximization procedure for our likelihood function, taking partial derivatives and eventually making this partial derivatives equal to 0 and solving this for mu bar and sigma bar. So in this particular case, our problem has a finite exact solution. Easy, well, more or less. The expressions which we encountered there were not that simple after all. But what do we do in the general case? In the general case, it is not a geometric Brownian motion. In the general case, there is no formula for the density. So, in general, let me put it another way. So, general case, not a geometric Brownian motion. We have a one-dimensional partial differential stochastic differential equation, dst equals to mu of st and t dt plus some function sigma of st and t dwt. So as we pointed out, in the general case, we still need this transition density function. P of, let's say, any point Si, conditional on the previous point Si minus 1, and the vector of parameters Q. And the vector of parameters Q will be here. Both mu and sigma depend on our vector of parameters Q. Okay, so we'll say Q here Q here. Okay, so in general, this probability density function can be obtained by solving numerically, by solving the Fokker-Planck partial differential equation. You remember? Solving the Fokker-Planck PD. The Fokker-Planck PD this density also depends on time ti, actually. So it does explicitly depend on time. So the Fokker-Planck PD would be dp dt, if you remember, equals to minus dds of mu of st times p plus 1/2 second derivative with respect to s of sigma squared, which is again a function of t, s and t, and obviously the vector of parameters q times p. That's our Fokker-Planck PD. With the initial condition, in the initial point at ti minus 1, p of s at ti minus 1, because we know that the value is equal to si minus 1 here, then the initial condition is a delta function, if you remember. It is a delta of s minus si minus 1. So by solving the Fokker-Planck PD numerically, you would be able to compute your probability density function, evaluate this probability density function in the corresponding point where you know the actual value si, and substitute into the log likelihood function. So then you would once again have the log likelihood function L of Q being sum from I1 to n log P of Si Ti, sorry, conditional on the previous point, conditional on the previous point, Ti minus, sorry, Si minus 1, in the previous point, Ti minus 1, and also conditional on our vector of parameters Q, generally speaking. Okay, and Q, and then this sum of logs is to be maximized over Q. But let us consider how in practice this scheme could be realized. So I invite you for a discussion. So first of all, we have this maximization problem. So we do need to maximize this likelihood function over the vector Q. In the simplest case, which we considered for the geometric Brownian motion, the vector Q contained two elements, mu bar and sigma bar, you remember. but in general, this vector can contain more parameters. A very realistic example in financial modeling would be a very realistic example in financial modeling would be if you, for example, for commodity prices, if you consider a model like, for example, your function mu of s and t, it may or may not explicitly depend on t, but let's say it is a trend. You mean revert to this trend. So the trend is linear, so it is at plus b, something like that, minus s. So this is some kind of linear trend. And also you have some non-trivial volatility structure. So there could be, for example, a function sigma of s and t. It may or may not explicitly depend on t, but let's say in a simple case, it is something like sigma itself, which is a function of t, times s to the power beta. Okay, I will use this as a constant for simplicity. And then we have our vector q consisting of the following parameters: kappa, a, b, sigma bar, and beta. By the way, if you remember, maybe we have mentioned, this volatility structure is called CV, constant elasticity of variance. A typical path of our stochastic process would look like the following. Here we have mean reversion to our linear trend at plus b, and therefore in general it would be something like that. So if it is t and a particular realization of our path st would be, we have a linear trend at plus b, and around this linear trend and mean reverting to this trend, is the path of our stochastic process with this volatility, which describes actually what our deviation from the path, how it would look like. And kappa is responsible to basically the speed of our mean reverting to the trend. So for example, if I draw up another, I use a different color, yes I can. If I select another color for that, just a second, it doesn't want to for some reason. No, doesn't work like this. Color picking function failed. Oh my god. I think the whole application has failed actually. I can't see my pen anymore. That's unfortunate. Then the idea was, okay, I can point to it, but I can't draw. Then the time of how quick you return to this trend, which is AT plus B, it depends on your kappa. So for example, here we can see visibly that there is a quick return. So we deviate from the trend AT plus B, and then we return quickly back to this AT plus B trend. We fall below the trend, then we return to the trend again, and so on. If the speed of mean reverting, of returning to the trend, is much less pronounced, so for example, deviating from the trend, then you very, very slowly decant to the trend, then possibly cross it. This would correspond to smaller values of kappa. So the larger kappa is, the more quickly you return to the trend. Your average characteristic time of returning to the trend is the inverse value of kappa. This type of model is a very, I would say, standard model in commodities, where you have some trend, you have some volatility structure, but you don't have an exponential growth like in the geometric Brownian motion. Commodity prices either return to a constant mean, or they return to slowly changing over time mean, like here, which is given by AT plus B. So in this particular case, we have 5 parameters, and with those 5 parameters, we really need to find them out to calibrate a model not with 2 parameters like it was for the geometric Brownian motion, but 5 of them. And with this non-trivial volatility structure, there is absolutely no way of how you can get a full closed form analytical solution for your density. So either you have to construct your density numerically using the Fourier-Planck partial differential equation, or maybe apply some approximations. And those approximations are going to be discussed in our current lecture. Okay, I will try to restart my screen. I'll drop it for a second and try to restart. You can still hear me, I presume. Okay. Are we? No. What shall we do? We do it that way. We start it again. And I will show you my screen once again. Okay, we have restarted. So let's discuss what we need to do in this case. So we are ending up with a quite computationally intensive procedure. So basically, once again, we maximize the likelihood function L of Q, which is a sum from I1 to N, N capital, log P of SI conditional on Si minus 1 and the vector Q. maximize it over Q. So first of all, how do we maximize it? Which maximization methods do you know? We need to maximize this function. Okay, this is a function of Q. What do you know from numerical methods, maybe from foundations of machine learning, from analysis? What would be the general method of maximizing this function? Which maximization methods do we know? Yes?
Gradient descent and grid search, maybe.
Good. You are right. You are right. So first of all, maximization methods are divided into two classes. And you are absolutely right that you pointed out to both of them. One class is called gradient-based, or more precisely, not only gradient-based, let's say derivatives-based. What is the difference? I will explain in a second. Derivatives-based optimization. In this case, it is not gradient descent, but formally speaking, because we are maximizing the function, it is a gradient ascent, right? In many methods like this, you would also compute not only the gradient, but you would compute the Hessian of this function. So yes, it is based on the function gradient L, which gives you the vector of your partial derivatives dl dq1 and so on, dl dq, let's say k, if there are k parameters altogether. So our vector q would be an element of Rk. In the example above, you remember when q was kappa a b sigma bar and better for commodities. Here k is 5. This is a popular commodity model. Very interesting from our current modeling perspective, trying to model, for example, the oil prices, oil future prices dynamics. And also high order derivatives, possibly. You are not limited to a vector of gradient. So for example, you would have Hessian of L, which is a matrix of second derivative, second order derivatives, dq1 squared, and so on. Second derivative of L with respect to dq1 dqn. It is symmetric. Here we have second derivative with respect to dqn dq1, which is obviously same as this. So it is symmetric around the main diagonal. Second derivative of L with respect to qn squared. That's our Hessian matrix. So typically our gradient-based methods, our derivative-based methods, they do require computation of a gradient and possibly computation of high-order derivatives, such as the Hessian, the matrix of second-order derivatives. And you can find multiple software implementations of those methods which require you to know the derivatives. but look at our function L of Q. And the problem is, if our P probability density function is computed using the Fokker-Planck partial differential equation, okay? Fokker-Planck PD, then it is a result of a numerical procedure. So basically you are on a numerical method in order to solve this Fokker-Planck PD, right? Then the question is, how would you be able to compute the gradient, or let alone the Hessian? The gradient and the Hessian are not computable analytically in that case, because there is simply no analytical formula. Your function by itself is numerically evaluated. Therefore, your derivatives, grad and Hess, may not be available analytically. And therefore, compute them by numerical differentiation. Alternatively, a completely alternative way, we would use derivative-free methods. And yes, grid search is one of them. And probably the easiest one. It is definitely a derivative-free method. There are others. Actually, derivative-free methods of global optimization, especially those implemented in free software, are not so easy to find. Although it is a very popular, common, standard problem, but not so many standard software solutions, especially open source solutions, are available. Grid search is a trivial one. What are the methods I can recommend? There is a method which is called MCS, and I really suggest that you pay some attention to this method and look at it. I think its current open source implementation is only available in MATLAB. MCS stands for multi-level coordinate search. And the idea of this method, it was developed at the University of Vienna, or Wien in German, Austria. You can find it. It is completely open source. The idea of this method is a very interesting one. First, it tries to approximate your function. For example, if for geometric reasons we consider a function to be a function of two variables, it tries to approximate your function over a certain region as a quadratic surface over that region. How? By computing the values of this function in some boundary points, and then approximating it as a quadratic surface. So basically your function to be maximized, L of Q, is approximated but only within a certain region. It is approximated as a quadratic function. What does it mean, quadratic function? It is something like you may have multiple Q variables, so it would be A, for example, there are K of them, if you remember, so it could be AK0 Q, basically in more general terms, let me put it that way. It would be in general quadratic polynomial in the quadratic polynomial in Q, so it would be, I can write it as sum of Aij Qi Qj, where Ij are from 1 to k, plus linear terms, sum from, let's say, I 1 to k, b I Qi, plus a constant term, plus c, approximate to the quadratic function. And for a quadratic function, of course, in a certain region of our parameters. And for a quadratic function, the maximum or minimum can be found analytically. So then obviously finding the max is trivial. The only problem is this maximum is not a global one. It is a maximum over a particular region of your parameters. So for example, if this is a Q1 and this one is a Q2, and this is your function L of Q, which you maximize. And in addition to the internal possibly existing maximum or minimum of this function, you also need to consider the values at the boundary in order to find the global maximum. And then you need to glue together those approximations constructed over different regions of Q1 and Q2. So for example, when you extend your region, then over the next region, you construct another quadratic approximation, which is somehow glued with the original approximation over the first rectangle area over the boundary separating them. So all this makes your approximations very, very involved, because you need to consider the maximum in the inner region plus possible values at the boundaries. Obviously, no one tells you how to select those approximating regions. You need to maybe merge them together, maybe other way around, make them smaller and smaller, which make this MCS method very complicated in implementation. But on the other hand, it has an advantage of after you have constructed the separation of the splitting of your parameter space into multi-dimensional rectangles, then you can find extreme points in the inner part of those regions by simply differentiating the quadratic approximations. So MCS is a very, I would say, interesting method. There was a competition, a shootout of global optimization methods, and MCS, I think at that point, it was about 10 years ago, had won this competition by a wide margin. There are some other derivative-free optimization methods, which I only mention here. So, for example, there is a method which is called direct. Implementation is available in C++ as part of the package called NLOpt for nonlinear optimization, and there is also an original implementation in Fortran. So there are some, and you see that either way, whether we use a derivative-free method or we use a derivative-based method, first of all, we need to evaluate our function in a large number of points. We evaluate our function L of Q. But now recall that evaluating our function L of Q is not a trivial thing either, because our function L of Q contains internally those logs of the probability density function. And in order to compute the probability density function, we need to solve the Fokker-Planck PDE. And that's a very big problem. Not only we run a numerical optimization method at the outer level, which is computationally intensive by itself, but internally, we also rely upon numerical solution of a Fokker-Planck partial differential equation, which is a very, very computationally intensive thing as well. I think at the end of one of our previous lectures, we considered at least an outline of how a partial differential equation can be solved numerically, again over grid. So for example, in this numerical setup, it might be that we are using grid methods twice. We are using grid method if, for example, not MCS or not gradient descent. We are using grid method in order to go through the grid of values of Q if the dimensionality of Q is not very high. For example, for 2-3 dimensions, it is okay. For 5 dimensions, using a grid method, grid search might not be a good idea. And then internally, for each point of the Q grid, we would use yet another grid method to solve the Fokker-Planck PDE and to obtain our function for the probability density P. So 2 nested grid methods would be required, or MCS with a grid method to solve the Fokker-Planck PDE, but nevertheless a very complicated procedure which would allow us to compute and maximize our likelihood function. I would like to stop at this point and ask you whether it is more or less clear what we are doing at the moment, and whether it is clear that the procedure is numerically very, very, very complicated. Please tell me what you think about this.
Well, it is clear for me.
Okay. In that case, we would probably be looking for something a little bit more efficient. Instead of solving the Fokker-Planck PDE, we still want some little bit more efficient way of how our function P can be computed. Obviously not exactly. The exact computation was possible when our process is a Brownian, standard Brownian motion with a drift geometric Brownian motion for simple analytically solvable stochastic differential equation, then yes, we could construct this function P analytically. In other cases, we can only do an approximation of P. And let us consider what kind of approximations we can do in this case. So I would say problem. Nested numerical evaluations outer level numerical maximization. Of L of Q. Inner level numerical solving of water plant PD to get P. So instead of this, we would like to construct some approximations. And you know what? These approximations can be constructed. So in a very simplistic case, let us consider an approximation which we'll call a locally normal approximation. It is a very, very, very trivial one. So locally normal approximation. What does it mean? Once again, let's consider our stochastic differential equation. So dst equals to mu of stt dt plus sigma of st and t times dwt. Okay. Now, what can we do? Locally normal approximation, so we are currently at point ti minus 1 with the value si minus 1, and we would like to get the probability density function of si at time ti, conditional on that si minus 1 and the vector of parameters q. We would like some approximation for that. What do we do? Very simple. Into our stochastic differential equation, into the right-hand side, take t equals to ti minus 1, st equals to si minus 1. So basically, we evaluate the right-hand side in the previously known point at ti minus 1. Then, what can we say? Approximately, what is dst? In this case, dst would precisely be si minus si minus 1. Would be approximately equal to the right-hand side mu evaluated in the previous point I minus 1. So mu of si minus 1 at time ti minus 1. Instead of dt, we write tau I, where you remember once again that tau I is a time difference. It is ti minus ti minus 1. Plus sigma of, again evaluating it in the previous point, si minus 1 ti minus 1. And for dwt, we would construct a random variable which I call zi, and this zi would be normally distributed, very much like dwt, would be normally distributed with zero mean and the standard deviation being the square root of tau I. So we use this approximation, basically substituting the previous point ti minus 1, si minus 1 into the right-hand side of our stochastic differential equation. So locally, in the vicinity of the previous point, ti minus 1, si minus 1, we assume that si minus si minus 1 is normally distributed. In this case, we can immediately say that si would be normally distributed as well, conditional on si minus 1. So si conditional on si minus 1 is also normally distributed, with the mean being equal to si minus 1 plus mu of si minus 1 ti minus 1 times 2i, and the standard deviation being equal to sigma of si minus 1 ti minus 1 times the square root of 2i. Okay? And if it is normally distributed, and obviously those mu and sigma implicitly depend on the vector of parameters q. So for clarity, let's write dependency on q here as well. They depend on q here. Okay. Because we now have a normal distribution, an approximate normal distribution, then we can use these formulas for the normal distribution density once again. What is very important? Why we call it locally normal approximation? It does not say and does not guarantee that Si is in general normally distributed. In most cases, it is not. We only say that it is normally distributed as an approximation conditional on the last observed point si minus 1, conditionally on that. When you move to the next point and you consider, for example, si plus 1, conditional on si, it would also be normally distributed, but with different parameters of this normal distribution. That's why at each point locally, we can approximate the distribution to be a normal one, but overall, because the parameters of those normal distributions change from one point to another, in general, T is not normally distributed. Locally, yes, globally, no. That should be pretty clear. And if we have this formula for the local normal approximation, then it is very easy, actually this one, then it is very easy to say what the probability density function is. Then the probability density function, which we insert into the likelihood function, P of Si Ti, conditional on Si minus 1 and yet the vector of parameters Q, would be given by this local normal approximation. So it would be 1 divided by the square root of 2 pi. Under the square root we have 2i. Outside the square root we have sigma of Si minus 1 Ti minus 1 multiplied by the exponent of minus 1 divided by 2 times 2i sigma squared, again of Si minus 1 2i minus 1 multiplied by the actual value Si minus the expected value, therefore minus si minus 1 minus mu of si minus 1 ti minus 1 to I minus 1 squared. So then we got some kind of analytical approximation. Obviously, this is only an approximation. Analytical approximation of our transition density. And then we can construct our likelihood function. So you remember that what we want sum from I1 to n log of this p, this one, of SITI conditional on the previous point si minus 1q to be maximized. And when we take log, the log, then up to constant terms, which we don't need, we get the following problem eventually. We get a function which I up to terms not depending on q, we get L tilde of q being a function, first of all, there would be, when we take a log, minus log sigma here, minus from the exponent. Therefore, dropping the minuses and going to the minimum rather than the maximum, there would eventually be sum from I equals to 1 to n log sigma of si minus 1 at the point ti minus 1 plus 1 divided by 2 times tau I sigma squared of si minus 1 ti minus 1 sigma squared multiplied by the same expression si minus 1 minus mu times of si minus 1 ti minus 1 times tau, sorry, tau I, not tau I minus 1, tau I squared. And this function is to be now minimized over the vector of parameters q, where the dependency on q is via our functions mu and sigma, which is now to be minimized over q. So we still need a numerical minimization method, in this case minimization. We still need to do either a gradient-based method or a gradient and Hessian-based method or a derivative-free method, for example, grid search, MCS, direct, whatever. So we still need a numerical minimization method. But the densities by themselves do not require Fourier-Planck PDE anymore. So we still need a numerical minimization, in this case minimization method. But fortunately, no Fourier-Planck PDE anymore. which is already a very big advantage, right? The only problem is, what do you think is a disadvantage of this method? We got rid of the Fokker-Planck PD. Moreover, you know, there is one more advantage, actually, a very significant advantage. Okay, tell me please, so what is one advantage and one disadvantage of the approximation we made? Any ideas, please? Turn on your microphones and tell me, please. One positive and one negative thing about the approximation we have constructed.
Well, one positive is that we don't need, well, we don't need any assumptions on sigma and mu for this equation. So
yes,
this is good.
Yes. So first of all, you're absolutely right. So we would say, well, first of all, one positive thing is that no Fokker-Planck. Plus, you say, you're absolutely right, works with general mu and sigma. Only need to assume that sigma is greater than 0. And again, you understand why, because now it's sigma appears under the log and also in the denominator here. So yes, it is a very good idea to assume that sigma is positive, right? That it wouldn't vanish. But apart from this assumption that sigma is positive, you don't need any special assumptions on sigma. There is one more very important positive thing about this, is that you see, after all, you do have a qualitative understanding of how it works. So we got a clear term structure. That's what I mean. We have a clear term structure of L of Q. So for example, you understand what happens if, let's say, our function sigma with some parameters q tends to 0. What happens when it tends to 0? Then log of sigma tends to minus infinity. So the first term would tend to minus infinity. The second term would tend to plus infinity instead, because it is positive, right? And sigma squared in the denominator would tend to 0, which means that probably you have, in this case, an undefined behavior, unless you really take this limit by using the mathematical methods, like in your first year mathematical analysis. But you understand that in general, if this term, for example, would tend to minus infinity, and this term would tend to plus infinity, as let's say sigma tends to 0, then somewhere probably there is a minimum. And that's precisely the minimum you would like to find. When sigma tends to plus infinity, then you have a different situation. Then the first term would tend to plus infinity, but the second term, because you now have sigma in the denominator, would tend to 0. So again, you can assume that there is a maximum or minimum somewhere. Well, probably the minimum, because overall the sum tends to plus infinity. So there is a minimum somewhere here, and probably a second minimum or maximum as sigma tends to 0. Obviously, without knowing the exact structure of sigma, you can't tell exactly what these limits are, especially the first limit, and where the minimum or maximum is. But at least you understand the role of your sigma, which appears under the log here and in the denominator here. And you understand the role of your term mu. So you have a term structure, which you can then possibly make more precise by substituting your exact model and investigating. But there is one big minus in this situation. What do you think is a negative? Feature of the approximation we have constructed. What is negative? Any idea why what we have done might not after all be a very good thing?
Well, maybe this approximation is very rude for some
Yes,
problems.
you're absolutely right. The approximation is really, really rude. And to understand why it is rude and to see if we can do any better than this, let's get back to the original stochastic differential equation and see what we have done there. So here we are. That's our stochastic differential equation, all right? So what we did, we substituted Si minus 1, Ti minus 1 into the trend and into the volatility term, here and here. What do you think? Where we got a larger error? By setting mu to a constant, substituting as in general, you see in between points I minus 1 and I, neither mu nor sigma is a constant one, but we made it a constant. We substituted the previous values Si minus 1, Ti minus 1 into both mu and sigma. So within this interval from point I minus 1 to the point I, we made both coefficients of our stochastic differential equation constant. And only the stochastic innovation, which is a Brownian motion tick, is not a constant. It is still a random variable, which we call Z in this case. In fact, it is the same as dwt. So what do you think? Where we made our approximation worse? By substituting the initial point of the interval Si minus 1, Ti minus 1 into mu, or by substituting same values into sigma? What is worse, do you think? They are not exactly equal. I mean, from the term of rudeness of our approximation. One has a greater impact on the quality of approximation, on decreasing the quality of our approximation than the other. Where do you think we are at fault? Mostly at fault.
Well, maybe at sigma.
Yes. First of all, yes, you are right. But obviously the second question is why at sigma?
Because maybe our distribution is based on Brownian motion, and sigma is the only thing that actually Oh, I forget this word.
Put it very simple. Actually, everything is in this line. You can already see it. The mu term, the trend term, however we approximate this term, is proportional to tau. So it is the overall term here is of the order of our tau I, right? Where tau I is our time step between ti and ti minus 1, the difference, ti minus 1, right? But the second term with sigma is proportional to zi, which is the same as dw Brownian motion increment, which is a normally distributed random variable of zero mean and the standard deviation being the square root of tau. And for this reason, this term is of magnitude of the square root of tau. You remember? And for the small values of tau, when tau is small, we would have that square root of tau is significantly greater than tau itself, right? For very small tau. You remember that in financial terms, typically tau, well, all temporal quantities are measured in years. Therefore, if in practice we observe our time series, let's say every day with a daily step using day intervalization, or maybe 1 hour using hourly intervalization, then tau I is significantly less than 1. And for the quantities which are significantly less than 1, yes, indeed, we have the square root being significantly greater than the quantity itself. Therefore, both mu and sigma are now approximations, but sigma is multiplied by, in general, a much larger value. It is multiplied by the value which is of the order of square root of tau. Therefore, any imprecision in sigma has a much bigger effect on the overall quality of approximation because it is multiplied by a larger value, right? Please tell me whether it is comprehensible. Here we multiplied, however, approximated mu by tau, which is small. But here we multiply again somehow approximated sigma by a random variable whose absolute value is of the order of magnitude square root of tau, which is much larger. This that I is a source of a much larger magnification factor. That's why any imprecisions in sigma would have a much more pronounced effect on the overall poor approximation of our probability density. So let's make this conclusion. Approximation is a rude approximation, which is true, and mostly due to fixing Si minus 1 to I minus 1 Ti minus 1 in sigma, because sigma is multiplied by O of square root of tau I, and mu is multiplied by tau itself, smaller. So basically what we need to do if we want to improve the quality of our approximation is to get rid of this approximation for sigma. No problem. Improve approximation for sigma. Okay, any ideas of how we can do that? Improving approximation for sigma. There are possible multiple ways of how we do it, but let me put it that way. If we know that sigma is a constant, then there is no problem in approximating sigma, all right? A constant sigma is a good sigma. Then there is no need to approximate, you know that it is a constant. Suppose that mu has become even more complicated, never mind. We are okay to introduce possibly extra errors in mu at the expense of getting sigma exact. Solution. Make sigma a constant. Can we do it? Yes, we can do it. Please tell me if you want maybe a 5-minute break and then we resume. Or we continue straight away. What's better for you? Do you want a break or not?
Yes, sure.
Yes, okay. Short break. Okay. Thank you. Okay, back to business. Can you hear me?
Yes,
Okay.
I can.
Okay, wonderful. We're continuing. So, how do you think we can make sigma a constant? You remember at some previous point, we have studied a magic tool which was called the eta-Dublin transform. You remember? So the way how we're going to do this is to apply the eta-Dublin transform by applying the eta-Dublin that way transform. Which transform? We don't know yet. But in general, let's say that we had the original variable st, and now instead of st, we will consider a new variable xt, which would be some function f, and this function f is to be found in general of st and maybe time explicitly. We'll see whether we need it or not. Probably f of st and t. So that in the original st space, we had, if you remember, dst was equal to mu, or sorry, mu without tilde. Why I put tilde here? Mu of st and t dt plus sigma of st t dwt. But in the new space for the new variable xt, we would have dxt being equal to some new trend, which I would denote by mu tilde, of xt and t plus constant. Which constant? It needs to be a positive constant. The volatility is positive, you remember. So without any loss of generality, let me say that this constant will be just 1. 1 times dwt. So this is a new constant wall. We would like to make our wall constant, possibly at the expense of more complex strand. Sorry, dt here, obviously. More complex strand dt. And in general, we should remember that our function mu depends on q and our function sigma depends on q, and therefore the new trend mu tilde would depend on q, on parameters q as well. So what do we do? And in that case, arguably, our function f, which represents the transform, would also depend on the vector of parameters q. So we don't know what f is, but let us just apply this transform with yet unknown symbolic f and see what we get. We would get by applying the eta-Dublin, we would get dxt is, first of all, partial derivative of f, our transform with respect to time, times dt, plus partial derivative of f with respect to s times dst, plus 1/2 second derivative of f with respect to s times dst squared. I hope you remember the e to Dublin transform, which is our best friend forever. Continuing, it is df dt plus, what is df ds? Well, we don't know yet. We just write df ds. And for dst, we would have mu of stt plus sigma of st t. I keep forgetting writing the dependency on q as well, but you understand we do depend on q. dt dwt here plus 1/2 second derivative of f with respect to s, and dst squared is obviously just sigma squared of st, t, and q times dt. Once again, you remember why. When we take the square of dst, we drop all terms of the order higher than dt. Square of the first term yields dt squared, which is dropped. The cross product 2 times mu sigma dt dwt yields a term of the order of dt to the power 3 over 2, which is dropped as well. And only the square of the final term, sigma squared times dwt squared, is rewritten as sigma squared times dt, because the expected value of dwt squared is precisely equal to dt. Therefore, by collecting the terms, we get df dt plus df ds mu plus sigma squared halved second derivative of f with respect to s squared times dt plus df ds sigma of stt q dwt. As we mentioned, we want the term at dwt to be identically equal to 1, right? Which we can actually get this way. The only thing we need to do to that end, let me move my screen. She's not exactly moving. More a little bit. Okay. So, in order to get this one being equal to 1, we simply have to do df ds as a partial derivative being equal to the inverse of our sigma st and q. And because sigma is positive, then the right hand side is also positive. It always exists and is positive. So that's yet another very good reason, you remember, why we want our sigma to be positive and bounded away from 0. From which it follows immediately that we can define the following function f as a function of s, t, and q, which will be satisfying all our conditions. F of s, t, and q is an integral from not necessarily S0 from any suitable initial lower bound, which I denote by S star arbitrarily. If S is positive, then sometimes it is convenient to use S star to be 0 if it is okay. If S is not positive, then we can use possibly minus infinity or some other value. We'll see. It really depends. S star is some arbitrary constant, which is a lower bound of integration to S of our inverse sigma of, I can't use the same integration variable here at the upper limit. So instead of S, I would write U, UT Q times du. Okay? Okay? Simply that. And if our sigma does not depend on t, then f would not depend on t either. We actually got what we want. Now let's finalize our partial differential, our stochastic differential equation for x. So in order to compute the new torrent, we need this. So what is the partial derivative of f over t? Then df dt is a similar integral from s star to s, but now of the partial derivative of sigma inverted with respect to t. So there would be minus du divided by the sigma squared of ut q d sigma dt. It's for this term. df ds, we already know that it is 1 divided by sigma. df ds is 1 divided by sigma. And finally, we need the second derivative, which is second derivative of f with respect to s squared, to s twice. If df ds is 1 divided by sigma, then it is obviously again minus 1 divided by sigma squared. D sigma ds. And then we get the following stochastic differential equation for x. We get dxt, which is a complicated term. So minus integral from s star to s d sigma of utq dt du divided by sigma squared of the same arguments, all right? Plus the second term is simply mu divided by sigma. The last term, we have sigma squared halved here and minus 1 divided by sigma squared here. Therefore, it is just minus 1/2 d sigma ds. Times dt plus 1 times dwt. Obviously, this trend is precisely what our new trend mu tilde is, but we need to express it back through x rather than s by inverting the transform. So this trend will denote precisely by mu tilde of xt and t. And now we have a stochastic differential equation for x, which precisely fulfills our objective. This stochastic differential equation does not, it has a sigma which doesn't depend on anything. It is a constant one. So for this SD for xt, we can now write again a locally normal approximation, but it is much more valid because we have a constant volatility. Now we use a locally normal approximation for xt. So there would be xi minus 1. And what is xi? Xi is f of si ti with our parameters q. Xi minus 1 is similar thing, f of si minus 1 ti minus 1 q. So we do know this values xi and xi minus 1. Would be equal to, yes, this approximated as mu tilde in the point xi minus 1 ti minus 1 multiplied by tau I plus 1 multiplied by, again, this random variable z, which has a normal approximation with 0 mean and the standard deviation being the square root of tau I. Okay? And then we can do what? We can construct the likelihood in a very similar way of how we have done it before. We can construct the likelihood function for x, right? Can we? And maximize this likelihood function with respect to x, maximize it with respect to the vector of our model parameters q. Okay? Can you tell me, please, can we do that?
Sure, we can.
Sure, we can, but it will be wrong doing that, I can tell you. We will be making a subtle, devilish, bad, difficult to find error in doing that. I will explain first qualitatively why this occurs, and then we'll correct this error and do a right thing. So, first of all, immediately the following step by itself is still okay. So can we say that in this case, the probability density function for x, p, I will call it px, so we distinguish it with ps, px of x I conditional on xi minus 1 okay, px at xi ti conditional on xi minus 1 and q would be equal to 1 divided by the square root of 2 pi to I. Now we have sigma being equal to 1, therefore nothing else here. Exponent of 1 divided by 2 times 2i, and that's all, without any sigma. xi minus xi minus 1 minus mu of xi minus 1 to ti minus 1 and q mu tilde squared. This is still okay, obviously, yes. If we have this type of approximation, this type of stochastic differential equation for x, then the locally normal density for x will be given by this expression. That's okay. What is wrong, however, is to consider the following problem. Lx of q, which would be equal to sum from I1 to n log px of xi conditional on xi minus xi ti conditional on xi minus 1q to be maximized over q. This is wrong. Why is it wrong? So the density for the process x we have obtained. Yes, it is correct. But constructing a very similar log likelihood function for x and maximizing it over q is wrong. Why? Any idea, actually? Can you guess? We're at a very important point. You know, it's even a seasoned professional doing a transformation like this can arrive at this Lx likelihood function, try to maximize it, and only then, much later on, realize that something is wrong. But I would like you to guess why actually, yes, we did E.T. Dublin transform. We arrived in the x random x stochastic process rather than s with a much more simple structure of the volatility, which is identically equal to 1. For that structure, we obtain the probability density function, and believe me, that's okay. But making the likelihood function out of that probability function is wrong. Why? No idea? Well, the idea is it is wrong because our F transform, which we used to get from S to X, may by itself depend on the parameters Q. But if I say that, it doesn't tell us anything, actually. So to understand why this is wrong, let us get to the very beginning of how we have defined the maximum likelihood estimator in the original S space, and then we'll see how we can correctly define it in the X space. This definition, which I put here, is incorrect. Don't use this maximization problem. It will yield a wrong value of Q. Don't do that. Let's get back. So basically what we did, you remember, we had a timeline. So back to the beginning. To understand of how to do it right. We had a timeline, and from t0 to tn, we had a path of our stochastic process, and suppose that this is ti minus 1, this is ti. At each point, we would be setting up some kind of range of the size dsi, which is fixed, infinitesimally small but fixed, and maximizing the probability of our whole path going through these ranges, you remember. So our original function L in terms of S of Q in log space, okay, it would be sum from I 1 to n log, let me even start with not a log likelihood function, but the general likelihood function without the logs. That would be more clear. So we read this. So the original likelihood function, would be L of Q, which is, you remember what? It is the probability of our path going through all these ranges at the corresponding ti. So that was a product from I equals to 1 to n of basically our probability density evaluated at point Si and Ti, conditional on the previous Si minus 1 and Q, times dsi. And this is actually nothing else but the probability of our random variable S at time ti belonging to the interval from Si to Si plus dsi, conditional on the previous point Si minus 1 and the vector of parameters Q, right? So in the original formulation, it was this, if you remember. Do you remember it from the last lecture, I think? All right? And then we would take the log, replace the product by the sum of logs, and arrive at the original, and arrive at the formula for log likelihood to be maximized. But the original formulation is this, where this P of SI/TI is actually the probability of our random variable S of Ti really belonging to the observed interval from Si to Si plus DSi, conditional on the previous point. Why only on the previous point is because of Markovian property, right? On the previous point, because of Markovian property. Okay. Now let's start with this once again and see how it would look like where these are infinitesimal, but const values. I will need to sharpen my electronic pen. So, what is this probability? Let's evaluate this probability very carefully. The probability of STI belonging to the interval from Si to Si plus DSi, conditional on Si minus 1 and Q. Now we apply the F transform equals to, you remember that our F transform is monotonic in S. You remember that X equals to F of ST and Q equals to the integral from S star to S du divided by sigma of U, T, and Q. Okay, the denominator is greater than 0. So first of all, the integral always exists. And secondly, because the integrand is positive, then this function is monotonically increasing in S. That's obvious, right? Therefore, the probability, because it is a monotonic function, then we can apply the monotonic function to both the left-hand side and the right-hand side of our inequality here. So we would say f of STI at time ti q would belong to the interval from f of Si ti q to the right-hand side, which is f of Si plus dSi ti and q, which will be the probability of, what is this? This is precisely xti as a random variable. Xti belonging to the interval, what is this? This is xi. What is this? F of Si plus dSi and so on. This is xi plus df ds times dsi. Okay. And by the way, we know that d of ds is nothing else but 1 divided by sigma. Therefore, this is the probability of, once again, ti belonging to xi plus dsi divided by sigma, which is for infinitesimally small dsi this is now the probability density function for x, px, evaluated in the point xi times dsi divided by sigma. And therefore, what we need to do actually is to maximize the following product from I1 to n of, more precisely, px of xi ti conditional on xi minus 1 and q dsi divided by sigma of si ti q. This is to be maximized over q. These are constants, same constants as before, and therefore we arrive at the following maximization problem, taking the log and we get eventually sum of I from 1 to n log px of xi ti divided conditional on xi minus 1 q. But now there is one more factor, 1 divided by sigma si ti q, and that one is to be maximized over q. In the original formulation, when we just applied blindly the maximum likelihood estimator to the transformed variable x, we would not have this factor. You remember, we only had this part. And that was a fundamental error. Why I said, don't do that. That approach is wrong. The right one is to use this type of estimator. And now the situation is actually a correct one. Moreover, let's get back to our estimator of the geometric Brownian motion and see that by doing a log transform in the geometric Brownian motion, we precisely get this transformation from S space into the X space. Example, GBM. Then sigma of ST was depending on S only. It was some constant sigma times S. Therefore, our function f, as we define it, x, which was a function of S, which would be an integral, if you remember, from any initial point S star to S, du divided by sigma bar u, which would be 1 divided by sigma log of S divided by S star. As I say, S star is arbitrary. So let S star being equal to 1. And therefore we would simply get log S divided by sigma bar. So basically this is exactly a kind of transform we wanted. You remember when we first from ST we're getting to log ST, then we would get from a log normal distribution to a normal one. So log ST is normally distributed. And finally, when we divide by sigma bar, we get this log ST to be normally distributed with whatever mean, and the wall being equal to 1 times square root of t. So that's exactly what we did in that particular example of the geometric Brownian motion, but here we have this in a much more general setup. So the question is, you know, we already have a pretty good, at least we believe, a pretty good formula for estimating our parameters. So now, again, we know what this px is under the log normal approximation. So now we can take it further once we got it correct. Again, I would like to dwell on this a little bit more. So looking into these two formulas, so we see this one, which contains division by sigma, is a right one. The one previously, which we had previously, which did not contain division by sigma, my scrolling doesn't work that well, is a wrong one. Okay? There is somewhere a formula which I say it is a wrong one. Wait a second, it will appear. Yes, you see the difference is that it doesn't contain division by sigma here. We say it is wrong. So once again, qualitatively, please explain who would venture to explain why this formula is wrong and the one which we obtained eventually is the correct one. By looking at the likelihood function here. Why we had to get back to our likelihood function, evaluate the probability of our STI getting into the interval from SI to SI plus DSI, and then deriving another formula in terms of X, which we claim is the correct one. So what is, how would you explain why this one is wrong, but the one which we eventually obtained is the correct one? It's actually much more important to hear your explanations here rather than going into any technical details.
Sorry, maybe because we blindly use S of I instead of X of I in probability.
Well, almost correct. Because we blindly used, you see, when we obtained our likelihood formula, we assumed that we had infinitesimally small but constant DSI here, right? In a similar way, if we're using this formula, we would assume that the corresponding dxi are constant. We simply drop them. They are arbitrary but constant, infinitesimally small but constant. But in fact, it is not true. If we originally assume that dsi are constant, then the corresponding dxi are not constant. They would be dependent on the parameters q. So the original ranges through which the interval through which our path would be going would become dependent on the transformation parameters. We can't say they are constant anymore. These are actually the values are dsi divided by the sigma. If sigma doesn't depend on the transformation parameters on q, then the two approaches would be equivalent. But under any normal situations, they are different. And because they are different, then we implicitly assume that our original dsi are constant, but this means that the corresponding dxi are not constant. And we had to derive them once again explicitly through the original probabilistic framework, and we ended up dividing by sigma. Whereas in this wrong approach, we would assume that dxi are constant, but dxi cannot be constant. Xi is not observable. Xi depends on actually the transformation we construct, and therefore the maximum likelihood approach by itself is not directly applicable to an unobservable value. So as a rule of thumb, just to summarize, in order not to get through the foundations of this maximum likelihood once again, we would say the maximum likelihood method is directly observable, is directly applicable only to the directly observable random variables, to the directly observable stochastic processes. Si is directly observable. That's why along the path of S, we can set up whatever DSI we want and later on make them constant and apply the maximum likelihood function to them. But Xi are not directly observable. They are obtained from Si through the F transformation, which contains yet unknown parameters. For not directly observable variables, the maximum likelihood method by itself is not applicable. You need to set up the maximum likelihood method in the original directly observable space, and only then transfer it into the final simplified space of X variables. So that would be a short explanation of why we do it that way but not the other. Okay? Now, once we found what the correct way is, we can derive the formula. Go on. Don't want to scroll back. Okay. We can now derive the formula of how in the X space we can apply this maximum likelihood. So it is the probability density function of X still divided by sigma. Therefore, our maximization problem in X will be, or actually minimization, will be the following. With simple transformations, you can now see that we would have sum from I equals to 1 to n the probability density function for x, which we already know what it is, log, of course, log of 1 divided by the square root of 2 pi to I, exponent of minus 1 divided by 2 times to I, and then obviously xi minus 1 minus mu tilde of xi minus 1 ci minus 1 and q to I squared, and not forgetting 1 divided by sigma of si to I. This one is to be maximized over q, or the following function, which we denote by L tilde x of q, up to constant terms which we drop, which will be sum of, 1 second please, I apologize for a small interruption. I will resume in a minute, need to respond. Okay, my apologies. Okay, I'm sorry, yes, getting back to our stuff. So what we got here, it is sum from I1 to n. These terms are not depending on any q parameters, and therefore we drop them, but sigma does depend on q. Therefore, what we have here is log of sigma of si minus 1 ti and q plus. So we see in the same function, for the sake of clarity, I have both actually si and xi variables, but because we know how to transform between them, it's no problem at all. 1 divided by 2 times 2i xi minus 1 minus mu tilde of xi minus 1 ti minus 1 and q squared, which is now minimized with respect to q. So that's what we wanted. This is an improved method. We still use a local approximation for the trend mu, but we do not use any approximations for, although there is a sigma here, but sigma it is only as a part of transform. Obviously, sigma is in mu tilde as well. So this approximation has much higher quality than the original one, which was locally normal in both mu and sigma. We can actually go a little bit further, and instead of using this locally normal approximation in the X space, we could go for a so-called heat kernel expansion and make it even more accurate, but by now expanding this mu structure in more detail. We can do that, but the whole idea is it's probably not that much important anymore. This maximum likelihood formula which we have obtained is already a fairly decent one, which allows us to estimate the model parameters. But I would like you, we're about to conclude today's lecture, I would like you to recall the following important definitions and properties of any statistical estimation. You remember the definitions of what we call biased or unbiased estimation. What is a biased or unbiased estimation? From your probability and statistics, do you remember?
Can you repeat the question, please?
There is a very important notion of biased versus unbiased estimators.
Well, biased is when n goes to infinity, and our estimated goes to our expected value of our estimated goes to some value, I guess.
Well, almost correct.
Yeah.
Actually, unbiased doesn't mean that this effect occurs when n goes to infinity. Unbiased means for any n, even a final one, you will have the property that the expected value of your estimated q must be equal to the real q. That means unbiased. If we have this expected value converging to the real values only as n tends to infinity, then it is, let's say, asymptotically consistent. That's what we would call, but not unbiased. So ideally, we would like it to be unbiased for any n, even finite n. So the question is, by applying this maximum likelihood estimator, for example, in the X space as we derived it, are there any guarantees that the estimator we have obtained is unbiased, or at least asymptotically consistent, just in general? And you know, the answer is, in general, no, because there is absolutely no way of how this can be proved in the general case. And indeed, there are counterexamples. So, in general, it is biased. And that is a big problem, because if it is biased, there are many different adverse situations which can occur here. So, for example, it might be that with respect to some Q components, the estimator is unbiased, but the standard deviation or variance of this estimator is so high that you typically get values well off the true values, although the expected value is still equal to the true value. That's also possible. So what we want is, first of all, this estimator to be unbiased, and then the standard deviation of the estimation itself tending to zero, as indeed, as you say, n tends to infinity, which means that the estimator is efficient. So there is a term of efficiency. In general, there is absolutely no guarantee that the estimator is efficient, or indeed the estimator is unbiased. So the question is, in general, in each particular case, when we have a particular model for mu and sigma, we can probably do extensive research and remove this bias. But I would like to ask you, we are now in data science rather than in statistics. By using data science methods, who can come up with a procedure, a numerical one, I would say data-centric one, data science-inspired procedure, which would allow us to convert this estimator which we constructed, this by maximization of L tilde x of Q, into an unbiased one. So suppose that we have a completely arbitrary mu and sigma for a particular model. What do we do in order to get an unbiased estimator? How can we make our estimator unbiased?
Well, maybe using bootstrap methods.
Using bootstrap methods. You are right. In general, you're absolutely right. So the general idea of the bootstrap methods, I would say, it is a whole family of methods, so multiple approaches are possible in this case. But a very, I would say, typical situation would be the following. You start with a particular known value of Q. So there are parameters which you know. You construct, by running a Monte Carlo simulation, you construct the path of your stochastic process. So you generate S and X values from T0 to Tn. You construct a path. You estimate your parameters back. And obviously, by doing this multiple times using different Monte Carlo passes, you can compute the expected value of your estimation. this expected value of your estimation will be different to the original values you started with, of course. And then you can construct some functions using machine learning methods which really tell you that difference. So basically using, for example, neural net, you can train this neural net to give you the difference between the actual value of your parameters q and the estimated value of q star. So basically by running Monte Carlo simulations on the original q, reconstructing the q parameters, computing the differences, computing the expected value of the differences, and then mapping the original values to the new values, you can construct a function in machine learning terms, which is the removing function, the function which removes the bias. I think that's precisely one of the ways of how machine learning and statistical learning come together. What I mean, you see, a very important point which I encourage all of you to think about and to discuss, and maybe we'll return to this point next time and discuss it. Suppose that we don't know any mathematical statistics. We say we are data scientists, we have machine learning methods, we have deep neural nets, other methods. These deep neural nets can learn whatever we want to learn. So then instead of minimizing this likelihood function, we would apply our machine learning methods in order to learn the values of q from the original values of s and x, just by using the machine learning methods like a neural net. So instead of, for example, maximizing this function or minimizing this function, can we simply train a neural net which would reconstruct the vector of parameters q from our time series s and x in general? In general, the answer is yes, of course, we can. Only, I would say, a direct blind application of machine learning methods to a problem about which we have absolutely no idea of the structure would yield, no doubt about that, very poor results. Because in fact, now by looking at this formula, we know the structure of our solution. Yes, you construct a function which has a log here, which has a quadratic term here. Then you minimize this function, so you know in general how you obtain your estimation q star. Even that one is imprecise. Even that one may be biased. But you have some regular procedure which guides you of how to do it, rather than relying upon learning it through a deep learning net, which is most likely and almost certainly not capable of doing that. So direct learning of your parameters from the time series cannot be achieved by a neural net. If you like, you can, by the way, try it out. But a much more regular function, much more, I would say, local, smooth, and better understood function, which is a bias correction function, yet that one can be learned. Don't try to solve, so my philosophical message in this case, don't try to solve a global problem using machine learning without understanding the structure of that problem. Solve it statistically first, construct a model, construct a statistical method of doing that, very much like we did in the final part of our lecture. And if some residual discrepancies still exist, like a bias in this case, which are supposed to be small and of regular structure, to correct them, apply the machine learning methods. So I would like you to think about this, and possibly some of you, if you are interested, to subscribe to a project which may lead to your final thesis, which would precisely be about a combination of machine learning and statistical methods. So I think this might be a very, very good idea to actually to explore in much more detail. Forgive me that I have forgotten the TOI here on this. Let us think about that. Okay.
Sorry, I have a question.
Yes,
this biasness, it responds to the model or the equation? Because what I don't understand is, all right, we have a model that is a neural network, and we do a lot of Monte Carlo simulations with different Q, and we somehow train our model to find this bias, right?
Yeah.
But why do we think that applying this model to the different set of data will yield us a good results? Why do we think that this bias?
First of all, the first part of your question, so you say where this bias would actually come from. Is it a result of our model being imperfect or the estimation method being imperfect? This is definitely through the estimation method. So the model may be perfectly correct. We may have constructed fairly accurately the time series for f and x based on our model, for example, applying a very small time step. But then the reconstruction method, after all, you see, this maximum likelihood, you can question it. Why actually would this be the only possible method if we set up some ranges of size DSI, maximize the probability of our path getting through these ranges? Yes, it sounds reasonable. It is probably a reasonable idea, but it is definitely not the only idea of how we can think about reconstructing the parameters of our process. So yes, the bias is due to limitations and perhaps conceptual limitations of the maximum likelihood method itself. There is simply no guarantee that this is the best method, and other methods do indeed exist, as opposed to the maximum likelihood. Why this bias correcting function might work? Because you see that up to a certain parameter, which might be, for example, the initial value of our process, let's say S0, all passes of our process are not part of the final result. So basically what we do, we have the set of parameters Q, and let's say, okay, the initial value of our process, which might be an extra parameter which we need to consider in the bias removal function. Then we generate the passes, we take the expected values, we map it back to the set of parameters. The path information is completely eliminated in this process. So we're really back to the original set of data we started with, modular the starting point. All path information has been eliminated by taking the expected value of our estimated Q stars. So for that reason, we really map basically the original set of parameters to the expected value of our estimations, removing any dependencies on the actual path, really by taking the expected value. And that's why there are good reasons to believe, although this needs to be verified by implementing this in practice, that this machine learning, or let's say nonlinear interpolation, which is the same thing in that case, method of removing the bias might very well be feasible. So I would really be interested if someone takes a courage to explore this in more detail, machine learning based bias removal methods. But for the moment, we are done. Any other questions? Okay, should we conclude our lecture then? If no more questions? Okay, I would like to thank you for your attention, and we'll meet next time next week. One more time. Thank you.